Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.1.2, Inverses via Euclidean Algorithm. So what I just showed you right here in subsection 4.1.1 was a description of a process which I call target inversion. I'm sure that other people probably do this, but um, at least intuitively in their heads and so forth, but I'm just giving it a name for the text. And if there's another name, maybe it may be there. However, I was um, unaware of it, but I thought of target inversion because um, we're targeting one. We're trying to get closer and closer to one. Let's take a look at Euclidean algorithm. This is a very common way of finding inverses, and it's nice for programming and writing algorithms. Um, let's look at an example here. Suppose we want to find the inverse of 7, say. Okay, 7 mod 32. Okay, so find the inverse of 7 mod 32. What are we going to do? Well, what we can do is right here, notice this line, this is like the division algorithm. Like 7 goes into 32 4 times, so 7 goes into 32 4 times, with a remainder of 4. So there's 4 more to add to get up to 32. So we can write down a line like this. Next, see these arrows? Let's just plop that there, put the 7 here, put this 4 here, and ask the same question between 4 and 7 that we did between 7 and 32. So 4 goes into 7 one time, then we add 3. Then we go again, get another line. So this 3 comes here, this 4 comes here, and we ask the same question for 3 and 4. 3 times 1 with a remainder of 1. We stop when this remainder is 1. Okay, so that's the schematic. If we want to find the inverse of 7 mod 32, we run a division algorithm, another one, and another one. Now notice when we do this, the remainder is always going to be less than what we're dividing by. So 4, okay, and the remainder is always less than that. The remainder is always less than that. So since we're always going strictly less than, eventually we will get down here to 1. If we get down to 1, there will be an inverse. If we never get to 1, there won't be an inverse. So, to find an inverse now, we have the full setup for what we're going to do, but we have a little bit of work then from there to do. And it's as follows. We take these 3 lines and we put bars all over them. We're working mod 32. But notice the top line is just 0 bar, right? 32 is multiple of itself. So 0 bar is equal to 4 bar times 7 bar plus 4 bar. Now, this top line, that's essential to realize that, because then you can rearrange this and solve for this remainder right here. So 4 bar, we solve for the remainder. And we just bring that over, we just got that, right? And because the 0 is gone, so it's just this. I mean, it's negative this, but the negative can come over under the bar. Okay, so we have this right here. So we've essentially taken what we had right here in this line and we found something for it. We take that result and we put it right here, like we follow these arrows. So we basically, using the idea that this is like 0, we solve for this 4, we take that result and we plop it in right here. Now we don't multiply things out, we just kind of keep things separate so we can kind of collect things a little bit, multiply things when we need to, but kind of the idea is that we're going to be rewriting everything in terms of multiplication by 7. Notice when we solve for 4, we rewrite it in terms of multiplication by 7. So this is now a multiplication by 7. And then this will become a multiplication by 7 as well, if we follow the line down. Now on this line, we do the same thing. We solve for 3, and notice we have a 7 right here, and then we have like multiplication by 7. Subtract it over, factor out a 7, Then 3 is in terms of 7 times something. So we have 7. So we pop that down here. We have like 7 times something and 7 times something. Subtract them over, factor out the 7. And we get 7 times something is 1. Kind of that was the schematic. Let's see that in action here in the text. So we solve for this, right? And then we go to the next line down and we can solve for 3, and we solve for 3. So let's see here. We have, okay, we solve for 3, but we're going to insert this in place of 4. Okay, so we have 4 there. We have 3. Okay, we've made the substitution here. And then we look at that. Okay, so we look at this line. So we're looking at this line right here. And we solve for 3 bar. We do that. We have 7. Then we and see this one, this is time, so it's just this. But then when we take it over, it becomes plus. So 3 bar is equal to 7 bar plus 4, 4 bar times 7 bar. We can factor out the 7 bar. We have 1 plus 4 bar becomes a 5 bar. So 5 times 7 is, in bars is 3 bar in this case. So we know 4 bar is this, 3 bar is that. Then we can use these two facts as we're going along. Remember, this becomes 4 bar right here, so we can use that right there. 3 bar was right here in the line going down, so that we have 1 bar is equal to this and this. Now we can think of this as 5 times 7 bar and then just subtract it over. So we end up getting this as a 1 bar, factor out the 7 bar. We have these, combine them, get negative 9 bar. Wow, we just found the inverse of 7 bar. Negative 9 bar times 7 bar is 1 bar. So we were able to compute that. Let's see. All right, now we're going to reverse this. We're going to look at 32 bar, which is the same as 4 bar in mod 7 arithmetic. Notice how we changed the color from red to green. That's because this red was mod 7. Or no, sorry, this red was mod 32, excuse me, was mod 32, and the green is mod 7. Okay, mod 7 for the green, and the red was mod 32. So we do, so here we, and we're going to use this exact same lines that we had over here. Use these same lines, but put green bars over everything. When we put green bars over everything, it's going to be representatives from 0 to 6 we'll be looking at, and they actually simplify very nicely. See right here. So right, 32 was 4 bar, right? 4 bar. Now 7 was right here. Now it's a 0, and so we get 4 and 4, just like we had up here. If we take a look at this, this was 4 and 4. Okay, so we just kind of put bars over everything on that line, and we have this to work with. Notice this is out, right? And let's see, because that's 0, right? Okay. The first line is extraneous. It doesn't tell us anything. All right, let's go to the next 2 lines and see what happens. So kind of what we want to do is we want to write 4 bar, everything in terms of 4 bar times something is 1 bar. So let's see if we can do that on this next line. Notice that we have a 0 bar now here. Why was that? That's because it was 4 and 4 moved down. Oh, so we get the 0 on the next line now. Ah, so before we had a 0 on the first line, but now when we reverse the tables, that guy comes down here, so we have a 0 on the second line. So we really start on the second line of that computation, and we go from there. Okay, all right. So let's do that. So we have 0 bar, and now we can solve for 3 bar in terms of 4 times something, right? And in fact, it's just 4 itself, and or negative 4, I guess, because it subtracts over. And then you take that, place it in, subtract, and then when you take it over, it becomes plus, and it's just 2 of those. And so it looks like 4 bar times 2 bar is 1 bar. So actually using the setup, same division line setup, we were able to find the inverse both ways. And it was awesome. So, all right. And here's a little theorem. So we have an inverse if and only if A and B share no non-trivial common factor. So they can't share any kind of factor other than maybe like one, or plus or minus. But that's pretty much it. So you can look through this theorem with a proof and kind of get an idea. But in the way we've kind of described it, maybe we've given some intuition for why this works. You can, but essentially the remainders are going down, and you can express the GCD um, in terms of so the GCD on each line, like A and B and R1 and A and so forth, all those GCDs are actually the exact same. And when you get down to the bottom, the last remainder actually ends up being the GCD of everything, the greatest common factor in that process. So you can take a look at that, greatest common divisor. Okay, so that concludes our discussion of subsection 4.1.2 in this read along, and the next one will be on multiplicative inverses that are polynomials. So in polynomial modular arithmetic, when we mod out by things like that. Thanks for watching.